In the spring of 2011, in a basement at the University of Toronto, a team of physicists pointed a camera at the most famous experiment in physics and photographed what every textbook in quantum mechanics had spent the previous century telling its students it was impossible to photograph. They photographed the paths that individual photons take through a double slit. Not inferred them, not represented them with mathematical diagrams, traced them. 80 trajectories, reconstructed from 41 imaging planes, published in the journal Science, showing on a printed page the actual routes that single particles took as they travelled from source to detector through two slits. And those trajectories told a story that should have rewritten the foundation of modern physics. They confirmed a prediction that had been made 84 years earlier in a hotel meeting room in Brussels by a French aristocrat almost nobody now remembers. So what does it mean that the most famous experiment in physics still has a layer in it that the textbooks refuse to teach? Get comfortable, subscribe if you have not, and stick around, because the picture we are about to draw of what a particle actually does between emission and detection is one your physics teacher was, almost certainly, not allowed to show you. Let us get into it. Part 1. The camera in the basement. There is a basement at the University of Toronto where, for the first time in the century-long history of the most famous experiment in physics, someone pointed a camera at the thing physics teachers had been telling students for 90 years it was impossible to photograph. The room is not particularly impressive. It is a working optics lab. There are grey steel tables with rubber feet. There are lasers on those tables, mounted on tiny brass posts. There is a cryostat in the corner that hums quietly to itself, because inside that cryostat is a tiny semiconductor crystal that has to stay at very nearly the temperature of liquid helium for the experiment to work. The crystal is the photon source. Every few seconds, a brief pulse of green laser light enters the cryostat, hits the crystal, and emerges on the other side as exactly one photon. Not a stream of photons, not a beam, one photon. The single most quantum of all quantum things, a particle of light so small and so alone that you cannot break it into pieces. That single photon then travels through a series of carefully arranged optical elements. It encounters a fibre that splits into two beams. It crosses a thin sliver of crystal, whose orientation has been chosen to extract a very small piece of information about what the photon is doing. It propagates through 8 meters of laboratory air. It lands on a cooled camera which records a single dot of light at the place where it arrived. Then the laser fires again, and another photon makes the same journey and lands somewhere else. Then another, and another. Tens of thousands of individual photons, each one alone, each one taking its own journey, each one landing as a single dot on the camera, until the team running the experiment has enough data to do something nobody had ever done before. They reconstructed the paths, not inferred them, not calculated them in the abstract, not represented them as theoretical lines on a diagram in a textbook. They drew, from the data those photons had given them, the actual physical trajectories that the particles had taken through the apparatus. 80 trajectories, plotted across the full 8 meters of the experiment, reconstructed from data taken at 41 different imaging planes along the way. The paper was published in the journal Science on the 3rd of June 2011. The authors were Sasha Coxis, Boris Braverman, Sylvain Ravez, Martin J. Stevens, Richard P. Mirin, L. Christa Schalm, and the senior physicist running the lab, a man named Ephraim Steinberg. The cover image of Science that week was a photograph of the trajectories, 80 curving, undulating lines spread across a field of soft blue interference, showing the routes that 80 individual photons had taken from source to detector through what amounted to a double slit. And here is the thing that made what they had done remarkable. The trajectories did not behave the way the standard textbook account of quantum mechanics says particles must behave in this experiment. They behaved exactly the way a French aristocrat named Louis de Broglie had said they would behave at a physics conference in Brussels in October of 1927. Each photon, according to the data, went through one slit. Not both. One. It had a definite position the entire time, and yet the interference pattern, the familiar wavy distribution of bright and dark bands that you see at the end of any double-slit experiment, the pattern that for a century has been treated as the central proof that particles do not have definite paths, that pattern appeared exactly as predicted. The photons that went through the left slit stayed on the left side of the apparatus. The photons that went through the right slit stayed on the right. No trajectory crossed the center line. They curved. They undulated. They clustered in the bright bands and avoided the dark ones, as though something was steering them, guiding them, as though something knew the geometry of the entire apparatus, both slits, even though each photon only ever passed through one. Physics World named the result the breakthrough of the year for 2011. It beat out the latest results from the Large Hadron Collider, which that year had reported the first hints of what would soon be confirmed as the Higgs boson. It confirmed a prediction that had been made 84 years earlier in a hotel meeting room in Brussels by a man who had been ignored by every important physicist in the world, and you have almost certainly never heard of it. Because here is what I want to tell you tonight, in the quiet hours of an evening when you have time to settle in and listen, and let your mind wander toward the strangest corners of the universe. You know the double-slit experiment. Or you think you do. You know the first layer, Thomas Young in 1801, demonstrating that light is a wave by showing that two beams interfere with one another and produce bright and dark bands on a screen. You know the second layer, the so-called observer effect, the discovery that if you try to detect which slit a particle is going through, the interference pattern vanishes, as though the particle itself somehow knows that it is being watched. These two layers have been taught in every physics class on every continent for the better part of a century. They are presented in textbook after textbook and lecture after lecture as the complete story. Layer 1, light is a wave. Layer 2, the act of observation changes what is observed. Together, these layers form the standard account of the most famous experiment in physics, and that account ends with what amounts to a shrug. We cannot know what the particle is doing between emission and detection. It does not have a trajectory. It does not take a path. To ask which slit it went through is to ask a question that has no meaningful answer. That is what you were taught. And it was never true. Not in the sense that the standard story was wrong about the data, because the data is correct. The interference pattern is real. The observer effect is real. The mathematics of quantum mechanics is the most precisely confirmed body of equations in the history of human thought. The story was wrong, instead, about what the data means, about what the data permits us to say about reality, about whether the question of what the particle is doing between emission and detection has an answer at all. There has always been a third layer. It was proposed in the same year that the standard story was being written, by a man who was standing in the same room as the men who wrote it. It was not refuted on mathematical grounds. It was not shown to be wrong by experiment. It was not replaced by something better. It was instead buried, deliberately, systematically, and for reasons that have nothing to do with physics and everything to do with personality politics and the enforcement of intellectual orthodoxy within a community that claims to value nothing but evidence. The third layer says this: particles do have definite positions. They do travel through one slit. They do follow specific deterministic paths. And the interference pattern exists because a real, physical wave passes through both slits at the same time and guides each particle to its destination. The wave is not a mathematical metaphor. It is not a convenient calculational tool. It is something in the world. Something that connects the configuration of the entire apparatus to the motion of every particle, and that operates non-locally, instantaneously, across any distance. This is not fringe physics. This is not pseudoscience. It is published, peer-reviewed, confirmed experimentally, and reproduced multiple times in the decades since. And the question you should be asking right now in 2026 is not whether it is true. The question is, why are the textbooks still the same? Why did your physics teacher never mention it? Why was a result that was named Breakthrough of the Year absorbed by the community and then quietly set aside, the way a family keeps quiet about a secret that everyone has agreed not to mention out loud? The answer to that question is a story that stretches back almost 100 years. It involves three of the most brilliant physicists who ever lived. It involves a woman whose careful mathematical analysis was buried in a journal that nobody read. It involves the only man who has ever been kicked out of America for being too good at physics. And it reveals something about the practice of science itself that the institution of physics would very much rather you did not know. The double-slit experiment does not just contain the mystery of quantum mechanics. It contains the evidence that the mystery was, in part, manufactured, that a simpler, clearer, more complete picture of reality was available from the beginning, and that the people whose job it was to tell you about that picture chose, in a quiet and consequential way, not to. This is the third layer. This is the story of how it was found and erased and found again. To get there, you and I are going to walk back through the early 20th century together. We are going to look at a hotel in Brussels in October of 1927, at a mathematics journal in Germany in 1935, at a small office at Princeton in 1951, at another small office at the University of São Paulo in early 1952, at a desk at CERN in the late 1960s, and finally at the basement in Toronto we began with. When we come back to that basement and see those 80 trajectories on the cover of Science magazine, you are going to understand, in a way that you did not understand when we began, exactly what was on those 80 lines, and exactly what it took to put them on paper. So let us begin. Not in Toronto, not in the basement. Let us begin where the standard story begins. Let us begin with what you have been taught, and let us look at it with a little more care than the textbook gives it. Because the second layer of the double-slit experiment, the layer about the observer and the strangeness of the quantum world, is not exactly wrong, but it is also not the layer you think it is. And once you see what it actually is, the existence of a third layer underneath it stops being a surprise and starts to feel almost inevitable. Part 2. The two layers you were taught. The standard story of the double-slit experiment begins in the year 1801 in London, at a meeting of the Royal Society, the oldest and most prestigious scientific organisation in the English-speaking world. The man giving the lecture that day was a physician named Thomas Young, and he was not technically a physicist. He was a doctor of medicine. But he was the kind of polymath that the late 18th century occasionally produced, and that the modern world, with its narrow specialisation, no longer has very much of. He had made contributions to medicine, to the study of elasticity in materials, to optics, to the decoding of Egyptian hieroglyphics. He had, in fact, helped decipher the Rosetta Stone. And on this particular evening in 1801, he was about to deliver a result that would eventually undermine the most authoritative figure in English science, a man who had been dead for 74 years, but whose authority still towered over the field. Isaac Newton, in his Optics of 1704, had argued that light was made of tiny particles. He called them corpuscles. He had a great deal of evidence for this view. Light travelled in straight lines the way you would expect particles to travel. Light cast sharp shadows, the way you would expect particles to cast shadows. Light could be slowed down or sped up depending on the medium it was travelling through, just like particles in a fluid. And because Isaac Newton was, by far, the most influential scientist who had ever lived, this view became orthodoxy for 100 years after his death. Light was a particle. Anyone who said otherwise was, by definition, on the wrong side of the question. Thomas Young, who was 30 years old and a Quaker, and had no particular reverence for Isaac Newton, decided otherwise. His evidence was not theoretical. It was experimental. He took a single thin beam of sunlight, the kind you might create by letting light through a tiny hole in a window blind, and he passed it through a barrier in which he had cut two very narrow slits, very close together. Then he let the light that emerged from those two slits fall on a screen on the other side. What he saw was not what Newton's particle theory predicted. Newton's theory would have predicted two bright stripes on the screen, one for each slit, the way you would expect if you fired two streams of tiny bullets through two narrow openings. What Young saw was something altogether different. He saw a series of alternating bright and dark bands stretching across the screen, with the bright bands brighter in the middle and tapering off in intensity toward the edges. He saw, in other words, an interference pattern, the kind of pattern you would expect if light were a wave, like a wave on the surface of a pond, and the two slits were producing two separate wavefronts that then interfered with one another, reinforcing in some places and cancelling out in others. This was the central insight of the wave theory of light. Where two crests of two different waves arrive at the same point at the same moment, they add together and produce a brighter point of light. Where a crest of one wave arrives at the same moment as a trough of another wave, they cancel one another out and produce darkness. The pattern of bright and dark bands on the screen was a direct map of the constructive and destructive interference taking place in the space between the slits and the screen. Light, Thomas Young argued, is a wave. It travels in wave-like pulsations. It interferes with itself the way water waves interfere with one another, and the interference pattern from the two slits was the proof. The British scientific establishment did not respond to this discovery with curiosity and enthusiasm. They responded with hostility. A man named Henry Brougham, who was at that point a young lawyer and political activist, who would later go on to become Lord Chancellor of Great Britain, wrote a series of anonymous attacks against Young in the Edinburgh Review. The attacks were unusually personal and unusually vicious for a scientific debate. They accused Young of being a charlatan. They accused him of misunderstanding the work of Isaac Newton. The attacks were so damaging that Young's publisher refused to put out a planned book on the subject. Young, who was a mild-mannered and somewhat reserved man by temperament, retreated to the practice of medicine and largely stopped publishing in physics. It took another 20 years before two French physicists, Augustin Jean Fresnel and François Arago, did follow-up experiments rigorous enough to confirm what Young had seen and to lay Newton's particle theory of light as the established orthodoxy of the field to rest. The wave theory of light became the new orthodoxy. The double-slit experiment, in its earliest and simplest form, was layer 1. Light is a wave. Interference proves it. The bright and dark bands on the screen are the signature of wave behaviour, and for nearly 100 years that was simply what the double-slit experiment meant. Then the 20th century arrived and everything fell apart. The story is one you may have heard. In 1905, a Swiss patent clerk named Albert Einstein published a paper showing that light, in certain experiments, behaved not like a wave but like a particle. He called these particles photons. He used them to explain the photoelectric effect, the phenomenon in which light shined onto a metal surface knocks electrons out of that surface. Einstein won the Nobel Prize for this work in 1921. So now light was a wave when you fired it through two slits, and a particle when you fired it at a metal plate. In 1924, a French aristocrat we'll be hearing much more about, a man named Louis de Broglie, published his doctoral thesis at the Sorbonne in Paris. In that thesis, he proposed that not just light but all matter has wave properties. Electrons, protons, atoms, anything with momentum has an associated wavelength. The shorter the wavelength, the higher the momentum. And in 1961, a German physicist named Klaus Jönsson, working at the University of Tübingen, took de Broglie's idea to its experimental conclusion. He machined two very narrow slits, each about 300 nanometers wide, into a thin sheet of copper foil. Then he fired a beam of electrons, accelerated to roughly 40 kilo-electron volts of energy, at the slits. The electrons hit a detector on the other side. The pattern that built up on the detector was an interference pattern. Bright and dark bands. Exactly the same kind of pattern that Thomas Young had seen with light in 1801 in London. Except now it was being produced not by light, which everyone could imagine as a wave, but by electrons. Electrons which had mass and electric charge. Electrons which were small particles. You could trap them in an electromagnetic field. You could count them one at a time. You could bounce them off the inside of a cathode ray tube. electrons were particles in the same way that pebbles are particles, and electrons, when you fired them through two slits, produced an interference pattern in exactly the same way that water waves do. Physics World, the magazine of the British Institute of Physics, conducted a reader poll in 2002 and asked readers to vote on the most beautiful experiment in the history of physics. Jönsson's two-slit experiment with electrons came in first place, but the version of the experiment that really turned the question of what is going on with this thing from a curiosity into a crisis came in 1989. A team led by a physicist named Akira Tonomura at the Hitachi Advanced Research Laboratory in Japan built a version of the experiment so clean, so precisely controlled, that they were able to fire electrons through it one at a time. One single electron at a time. The electron travels through the apparatus, hits the detector as a single dot, a single point, unambiguously a particle. Then the next one, another dot, at a slightly different position on the detector, then another, and another. At first the pattern of dots on the detector is essentially random, no structure, just scattered points spread across the screen. After 20 minutes, after tens of thousands of single electrons have each individually travelled through the apparatus alone, and each individually arrived at the detector alone, the pattern emerges. Bright bands where the dots cluster densely. Dark bands where almost no dots have fallen. The interference pattern, the same kind that Thomas Young saw, the same kind that Klaus Jönsson saw, has built itself up dot by dot from individual, isolated, single particle arrivals. Now think for a moment about what this means. Each electron arrives as a particle. There is no ambiguity about that. The detector clicks. The dot appears at a definite location. Each individual electron is, in every observable sense, a particle. But the pattern, the collective distribution of where those electrons are landing, is a wave pattern. It is as if each electron all on its own knows where the bright bands are supposed to be, knows where the dark bands are supposed to be, knows about the existence of both slits, even though it can only have gone through one of them. As if the wave is somehow guiding the individual particles, telling each one where it is allowed to land and where it is not. This is the moment, in the standard textbook account, when the second layer of the double-slit experiment gets introduced. The second layer is what physicists usually mean when they say that quantum mechanics is weird. It is the layer about the observer. In 1991, a group of physicists led by Marlon Scully, working with Berthold Georg Englert and Herbert Walter, published a paper in the journal Nature showing something even more disturbing than the original result. They showed that you can, in principle, set up the experiment in such a way that you would be able to determine, after the fact, which slit any given particle had gone through. You do not actually have to look. You only have to set things up so that the information is, in principle, available. And the moment you do, the interference pattern disappears. The bright and dark bands go away. The pattern on the detector becomes the kind of pattern you would expect from particles fired through two slits, with no interference, just two bumps, one behind each slit. Even more strangely, if you then erase the which-way information before looking at it, even after the particles have already hit the detector, the interference pattern comes back. This is called the quantum eraser. It is the phenomenon that the philosophy of physics has been trying to digest for the last 40 years. In 2000, a team led by a physicist named Yoon-Ho Kim took the quantum eraser one step further. They built a delayed choice version, in which the decision to erase or preserve the which-way information was made after the particle had already hit the detector. Far enough after that, in a strict sense, you could say the decision was made in a region of space-time that was causally disconnected from the particle's arrival, and still, the interference pattern's presence or absence on the detector matched the decision that was made later, as though the decision somehow reached backward in time to determine what the particle had done. Every popular science account of the quantum eraser treats this as evidence of cosmic strangeness, as evidence that reality, at the quantum scale, is genuinely outside the bounds of ordinary causation, as proof that the future can influence the past, or that consciousness creates the world, or that the universe is fundamentally and irreducibly beyond our comprehension. And if you accept what is called the Copenhagen interpretation of quantum mechanics, the framework in which all of this is usually presented, then it is, yes, that's strange. But there is another reading of the same data, a reading that was available in 1927, a reading that was available more famously in 1952, a reading that, as we will see, the experiment in Toronto in 2011 gave a great deal of weight to. In that other reading, the photon always had a trajectory. The eraser did not reach back in time. The correlations between the two entangled photons that the experiment depends on were built into the joint wave function from the moment of their creation. The weirdness in this reading does not exist in reality. It exists in an interpretation that refuses to assign definite properties to particles, and then finds itself confused when the outcomes of experiments behave as though particles had definite properties all along. The quantum eraser is only paradoxical if you start from the Copenhagen interpretation. If you start from pilot wave theory, the quantum eraser is straightforward. It is just two entangled particles, each one following a definite trajectory, with their joint wave function evolving in a perfectly normal way, according to the equations of quantum mechanics. But nobody told you that the other reading exists. That is the central point. The second layer of the double-slit experiment is real. The data is correct. Detecting the which-way information does destroy the interference pattern. That is a reproducible, undeniable, important experimental fact. But the interpretation, the claim that the particle did not have a path, the claim that the question of where the particle was between emission and detection is meaningless, the claim that reality at the quantum level is irreducibly random, all of that is not data. It is a philosophical position. It is a position that was adopted by a specific group of people at a specific moment in history. And at that exact moment, in that exact room, someone was standing up and proposing a different position, a position that fits the data just as well, and asking the room to listen. The room did not listen. That meeting is where this story really begins. So you and I are going to go to Brussels in October of 1927, and we're going to sit in the back of the room while the most important conversation in the history of physics takes place. And we're going to pay close attention to the man who lost the argument, because the man who lost the argument was right. The room, with the most brilliant collection of physicists ever assembled, was wrong, and the room moved on. Part 3, Solvay, October 1927. The 5th Solvay International Conference on Electrons and Photons opened on the 24th of October 1927 at the Hôtel Métropole in Brussels. It was hosted, as the Solvay conferences had been since their founding in 1911, by an institute that the Belgian industrialist Ernest Solvay had set up to bring the most important physicists in the world together once every few years and let them argue. 29 physicists were invited. 17 of them either had already won or would later win the Nobel Prize in Physics or Chemistry. The photograph taken that week of those 29 men and one woman, arranged in 5 rows in front of a stone facade, is the most reproduced image in the history of science. There is Hendrik Lorentz, the chairman of the conference, in the centre of the front row, 74 years old, with 1 year left to live. To his left, the only woman in the photograph, Marie Curie, who at that point was the only person in the world who had won the Nobel Prize in 2 separate sciences. To his right, Albert Einstein, 48 years old, his hair still mostly dark, looking faintly bored. Behind them, the second row contains Max Planck, the founder of quantum theory, and Niels Bohr, the founder of what would become the dominant interpretation of quantum theory. The third row has Erwin Schrödinger, Wolfgang Pauli, Werner Heisenberg, and Paul Dirac, 4 of the men who, between them, had constructed the modern mathematical framework of quantum mechanics in the previous 2 years. And in the back row, standing with the others who had not yet been given any seat of honour, is Paul Ehrenfest, a friend of both Einstein and Bohr, who would, by the end of the week, scribble on a blackboard in the conference room a comparison to the Tower of Babel, because everyone was talking and no one was listening, The official subject of the conference was electrons and photons. The actual subject was a war. On one side of that war stood Niels Bohr, who was 42 years old, and his closest collaborators. Werner Heisenberg, who was 25 and had, 2 years earlier, written down the equations of matrix mechanics, the first complete mathematical formulation of quantum theory. Max Born, who was 44, who had given Heisenberg's equations their interpretation in terms of probabilities, and who had laid out the rule that the square of the wave function gives you the probability of finding a particle at a given location. Wolfgang Pauli, who was 27, who had derived the exclusion principle that explains the structure of the periodic table, and who was famous within the field for being so sharp-tongued that other physicists were afraid to present talks when he was in the room. These 4 men, in the 2 years leading up to the Solvay conference, had built quantum mechanics into a working physical theory, complete with mathematical formalism and predictive power. And they had arrived at a philosophical conclusion that, in their view, was a necessary consequence of the mathematics. The wave function, they argued, does not describe physical reality. It describes our knowledge about physical reality. Particles do not have definite properties until they are measured. The act of measurement does not reveal what was already there. It creates the outcome in the moment of measurement. Randomness, in this picture, is not a feature of our ignorance. It is a feature of nature itself. The universe, at its base, is not deterministic. It is probabilistic. And there is no point in asking what is happening between measurements, because between measurements there is, in some real sense, nothing definite to ask about. On the other side of the war stood 3 men. Albert Einstein, 48, who at this point had spent 10 years trying to find a way to reconcile his discomfort with quantum probabilities and his recognition that the theory was mathematically working extremely well. Erwin Schrödinger, 40, who had derived the famous wave equation a year and a half earlier, and who, although his equation was the central piece of the new theory, had become increasingly uneasy about how Bohr and Heisenberg were interpreting his equation. And the third man, a 35-year-old French aristocrat named Louis de Broglie, who would 2 years later receive the Nobel Prize for his discovery that matter has wave properties, and who at this Solvay conference was about to make a proposal that would, if accepted, have changed the entire course of 20th century physics. De Broglie was an unusual physicist. He had been born in 1992 into one of the oldest and most aristocratic families in France. The de Broglie family had been prominent since the 17th century. They held both a French ducal title and a princely title that they had received, several generations earlier, from the Holy Roman Empire. Louis would, eventually in 1960, become the 7th Duc de Broglie upon his elder brother's death. But in 1927 he was still simply a research physicist, working in the laboratory that his elder brother Maurice had set up in the family mansion in Paris. He had originally studied history at the Sorbonne, earning his degree in 1910 at the age of 18. He had only switched to physics later, drawn into the field by his brother's work on X-rays. During the First World War he had been stationed at the Eiffel Tower, working on military radio communications for the French army. It was one of the stranger apprenticeships in the history of science. A future Nobel laureate learning about waves and oscillations by helping the French military signal corps communicate from the top of a steel lattice in wartime Paris. His doctoral thesis, which he had defended in November of 1924 at the Sorbonne, had proposed something that the thesis committee was not entirely sure what to do with. He had proposed that every particle in the universe has, associated with it, a wave. The wavelength of the wave is determined by the particle's momentum. The faster a particle is moving, the shorter its associated wavelength. This was not a vague metaphor. It was a precise mathematical relationship, and it was the foundation on which Erwin Schrödinger, 2 years later, would build his wave equation. The mathematician on the thesis committee, Élie Cartan, was uncertain. The physicist on the committee, Jean Perrin, who would himself win the Nobel Prize in 1926, did not know what to make of it either. De Broglie's advisor, Paul Langevin, sent a copy of the thesis to Albert Einstein in Berlin and asked for an opinion. Einstein wrote back with a level of enthusiasm that Langevin had not been expecting. He told Langevin that the thesis was, in his judgment, a major contribution. He sent the thesis on to Erwin Schrödinger with a personal recommendation, and Schrödinger, working from de Broglie's foundation, derived the equation that bears his name. Without de Broglie's 1924 thesis, there is no Schrödinger equation. Without the Schrödinger equation, there is no quantum mechanics as we know it. The entire mathematical framework that the Copenhagen group used at Solvay to argue that particles do not have definite trajectories was, ironically, built on top of de Broglie's insight that particles have wave properties. At Solvay, in October of 1927, 2 years before he won the Nobel Prize, de Broglie presented something far more radical than wave-particle duality. He presented a complete physical picture of what the particle and the wave are actually doing. His talk was titled, in French, La Nouvelle Dynamique des Quanta, the new dynamics of quanta. And what he proposed was this: the particle is real. It is a real, point-like object with a definite position at every moment of its existence. The wave is also real. It is a real physical wave, evolving in space and time according to the equations of quantum mechanics, the equations Schrödinger had just derived. Both of these things exist simultaneously all the time. The particle has a definite trajectory. The wave evolves alongside it. And here is the central new piece. The wave guides the particle. The wave tells the particle where to go. He called it the pilot wave. The particle is the boat. The wave is the pilot. The boat is steered at every moment by the pattern of the wave around it. Think for a moment about what this means for the double-slit experiment. In de Broglie's picture, when you fire a single electron at 2 slits, the pilot wave, the wave that is associated with the electron, passes through both slits simultaneously. The wave does what waves do. It interferes with itself on the other side of the barrier, creating a landscape of constructive and destructive interference, bright zones where the 2 wavefronts reinforced one another, dark zones where they cancelled out. But the electron itself, the actual particle, passes through only one slit. It has a definite trajectory. It has a definite position at every moment. The interference pattern of the wave on the other side of the slits is then read by the electron in some sense, and the electron is steered toward the bright regions, the regions where the wave has constructively interfered with itself, and away from the dark regions, the regions where the wave has cancelled out. Over many electrons, each one starting from a slightly different initial position, because we cannot know the initial conditions exactly, the collection of final positions on the detector reproduces the interference pattern. The wave makes the pattern. The particle rides the wave. The pattern is built up from particles whose individual journeys are deterministic, but whose collective distribution looks wave-like, because each particle has been guided by a wave that explored both slits. There is no mystery. There is no collapse of the wave function. There is no need to declare that the electron goes through both slits simultaneously. There is no need to say that the question of which slit it went through is meaningless. The answer is clear, definite, and deterministic. The electron went through one slit. The wave told the electron, through its influence on the electron's motion, where to go. And the interference pattern on the detector is the natural result. De Broglie presented this picture, in detail, with the mathematics worked out, to the most brilliant collection of physicists who would ever be in one room together. He explained how the pilot wave passes through both slits, while the particle goes through one. He explained the role of the wave in guiding the trajectory. He answered the question of why the interference pattern looks the way it does. And then Wolfgang Pauli, who was sitting in the audience, stood up and raised an objection. Pauli's objection was a technical one. He argued that de Broglie's framework, in the form de Broglie had presented it, could not properly handle inelastic scattering, the process in which a particle interacts with another particle, and they exchange energy, and one of them changes its quantum state. Pauli's objection has been repeated in textbooks for the last 80 years as the moment when de Broglie's theory was conclusively shown to be wrong. The story, as the textbooks tell it, is that Pauli demolished de Broglie at Solvay, and de Broglie had no answer. This is not what happened. In 2009, two scholars named Guido Bacigalupi and Anthony Valentini published a book called Quantum Theory at the Crossroads, which contained, for the first time in English, a complete and careful translation of the proceedings of the Fifth Solvay Conference. They showed, going back to the original transcripts, that de Broglie did answer Pauli. He explained correctly how the apparent problem dissolves once you consider what happens when wave packets in configuration space separate during a measurement. Léon Brillouin, who was also in the audience, supported de Broglie and responded to Pauli as well, agreeing with de Broglie's analysis. The correct answer was given. It was given in the room. It was preserved in the official conference proceedings. Pauli himself, before Solvay, had written to Niels Bohr describing de Broglie's work as, in his words, very rich in ideas and very sharp. And yet, after Solvay, the verdict on de Broglie's proposal had been determined, and the verdict had almost nothing to do with the mathematics. The verdict was that the Copenhagen group, the group around Niels Bohr, had won. They had not won because their argument was more mathematically rigorous than de Broglie's. They had not won because they had identified a fatal flaw in his theory that he could not answer. They had won because they were louder, more organised, more confident, and more numerous. Bohr was a charismatic personality who collected acolytes the way some people collect stamps. Heisenberg, Pauli, and Born were young and intellectually aggressive and quick on their feet. The institute that Bohr ran in Copenhagen, with its mixture of free intellectual exchange and total philosophical conformity, had been training a generation of younger physicists who would soon be filling the faculties of the major universities of Europe and eventually the United States. The Copenhagen interpretation had momentum on its side, and personality on its side, and the seductive intellectual flair of being the answer that the smartest young people in the field were excited about. De Broglie, by contrast, was an aristocrat. He was quiet. He was mild-mannered. He preferred reading and thinking and writing to debating. He was not a natural fighter. He did not have a team of acolytes ready to push his ideas at every conference. He had presented his picture in detail with the mathematics worked out. He had answered the only serious technical objection that was raised. And then, as the conference moved on and the corridors filled with conversation, he found himself standing alone. The argument in the room had ostensibly been about the mathematics of inelastic scattering. The argument in the corridors was about which interpretation of quantum mechanics was going to define the field going forward. And the Copenhagen group, by the end of the week, had taken the corridors. The room moved on. What happened next is what makes this story not just a historical curiosity, but a tragedy. De Broglie went back to Paris. Within a year, the consensus that had formed at Solvay had hardened into a near-religious orthodoxy. The Copenhagen interpretation became, simply, what quantum mechanics meant. The pilot wave theory became, within a few years, a footnote, a curiosity that some old French nobleman had once proposed and that nobody serious took particularly seriously. De Broglie did not push back. He was offered a chair at the Sorbonne, and he took it, and he began teaching quantum mechanics to French students. And what he taught them, for the next 25 years, was the Copenhagen interpretation. He taught them that particles do not have trajectories. He taught them that the question of where an electron is between emission and detection is meaningless. He taught them, in other words, the interpretation that said his own theory was wrong. For 25 years, the man who had the answer, the man who had presented it to the most powerful physicists in the world, the man who had defended it correctly against the only serious objection that had been raised, taught his students the interpretation that buried it. The social pressure was too great. The intellectual climate was too hostile, and as we'll see, there was another piece, a piece that had not yet fallen into place at Solvay, that made the situation feel, to anyone in the field, completely closed. That piece was a mathematical proof, a proof that hidden variable theories of the kind de Broglie had proposed were not just wrong but impossible. The proof was published in 1932 in Berlin by a mathematician who was, at that point 28 years old, and who would become, in the decades that followed, one of the most influential figures in the history of mathematics and computer science. His name was John von Neumann, and his proof was wrong. Part 4. The Wrong Proof and the Woman Who Caught It. In 1932 in Berlin, a young Hungarian mathematician named John von Neumann published a book called Mathematische Grundlagen der Quantenmechanik, the mathematical foundations of quantum mechanics. Von Neumann was, by any measure, one of the most brilliant mathematicians of the 20th century. He would later, in America, become a central figure in the Manhattan Project, in the early days of computer science, in game theory, in the theory of self-replicating machines. His ability to do mental arithmetic and to handle abstract formalism was, even among the great mathematicians of the era, exceptional. And in 1932, in this book, he set himself the task of placing quantum mechanics on a rigorous mathematical foundation. He largely succeeded. The Hilbert space formalism that physics graduate students still learn today is, in its basic form, von Neumann's formalism. Buried in the book, in a chapter near the end, was a section presenting what von Neumann claimed was a rigorous mathematical proof of an extraordinary statement. The statement was this: no theory in which particles have hidden definite values for their physical properties before measurement, no theory of the kind that Louis de Broglie had proposed 5 years earlier at Solvay, can ever reproduce the predictions of quantum mechanics. In other words, hidden variable theories are not just wrong, they are mathematically impossible. Von Neumann had derived this conclusion from a small set of mathematical axioms that he had assumed about how quantum measurements must work. The proof was treated by physicists who read the book as mathematical gospel. For the next 30 years, the von Neumann impossibility proof was cited, in textbook after textbook, in research paper after research paper, as the reason why de Broglie's pilot wave theory, and any theory like it, was not just unfashionable, but actually mathematically forbidden. The case was closed. You could not give particles definite positions and trajectories and still get the right answers. Von Neumann had proved it. The proof was wrong. And the way in which it was wrong was, by the standards of professional mathematics, embarrassing. Von Neumann had assumed, as one of his axioms, that for any two physical observables in a quantum system, the expectation value of their sum must equal the sum of their expectation values. For observables that commute, observables that you can measure simultaneously, this is obviously true. But for non-commuting observables, the observables that are at the heart of quantum mechanics, observables like position and momentum where the uncertainty principle applies, this assumption is exactly the kind of thing that a hidden variable theory would not satisfy. Von Neumann had, in effect, smuggled the conclusion he was trying to prove into the axioms of his proof. He had assumed, without justification, that hidden variables behave in a certain way, and then he had derived from that assumption that hidden variable theories cannot work. It was a circular argument. The proof did not prove anything. In 1935, a young German mathematician named Grete Hermann noticed this. Hermann had been trained at the University of Göttingen, where she had been a doctoral student of Emmy Noether, one of the greatest mathematicians of the 20th century. Noether's name today is most associated with Noether's theorem, the result that links symmetries in physics to conservation laws, but she was, in addition, a pure mathematician of staggering depth, and her training of her doctoral students was famous for its rigour. Hermann brought that rigour to the analysis of von Neumann's proof. She published her analysis in 1935 in a paper titled Die naturphilosophischen Grundlagen der Quantenmechanik. The paper appeared in a small specialized German journal called the Abhandlungen der Friesischen Schule. This was a neo-Kantian philosophy journal. It was a journal that physicists, as a rule, did not read. It was a journal that most university libraries did not subscribe to. In her paper, Hermann laid out, in careful and rigorous mathematical detail, exactly where von Neumann had gone wrong. She showed that the assumption about expectation values was unjustified for non-commuting observables. She showed that the conclusion that hidden variables were impossible had been smuggled into the axioms from the start. She showed, in other words, that the proof proved nothing. Nobody read it. Or rather, nobody who would have cared about it read it. The journal was obscure. Hermann was a woman in Nazi Germany who was also politically active in the resistance, which put her under Gestapo surveillance and made academic publication, for her, even more difficult than it was for anyone else in her position. Within a year, she would have to flee Germany to avoid arrest. Her paper sat in the bound volumes of a journal nobody read, in libraries that did not always order the next issue. For the next 30 years, the physics community continued to cite the von Neumann impossibility proof as the reason hidden variable theories were forbidden, while a careful and correct rebuttal of that proof sat unread in a German philosophy journal that they had never heard of and could not have found even if they had wanted to. The rebuttal was finally found independently in the early 1960s by a physicist at CERN named John Stuart Bell, who would in 1964 derive the theorem that bears his name. Bell, on reading von Neumann's proof carefully for the first time, was incredulous. He could not believe that the entire field had built its philosophical orthodoxy on a proof whose central assumption was unjustified and whose conclusion was circular. He called von Neumann's argument, in his later writing, not merely flawed but foolish. And when he learned, soon afterward, that Greta Hermann had identified the same flaw 30 years earlier and that her paper had been ignored, his incredulity became fury. He understood then that what had happened to de Broglie at Solvay, and what had happened to David Bohm in 1952, and what had happened to the question of hidden variables in general for the entire middle third of the 20th century, was not the result of a careful weighing of evidence. It was the result of a social and institutional consensus that had been propped up for 30 crucial years by a wrong proof that the field's leaders had simply not bothered to check. The wrong proof, in other words, was not just an embarrassment, it was an instrument. It was the mathematical artifact that made it possible for the Copenhagen interpretation to claim, with apparent technical authority, that it was the only interpretation possible. Take away the proof, and the situation looks completely different. Take away the proof, and Copenhagen becomes, suddenly, just one philosophical position among several, with no privileged mathematical claim to be the only one. The proof, for 30 years, was the lock on the door. And the woman who had picked the lock in 1935 had been unheard. The fact that she was a woman, in Germany, in the 1930s, doing rigorous mathematical work in a philosophy journal, is part of why the lock stayed closed. By the time the field caught up to her analysis, two more crucial things had happened. The Second World War had killed many physicists and reshaped the institutional landscape of the field, and a man named David Bohm, who had never read Greta Hermann's paper and who had never seen de Broglie's Solvay presentation in any detail, had independently arrived at the same conclusion, from a completely different direction, 25 years later. While teaching the Copenhagen interpretation himself in the most prestigious physics department in the world, Bohm's story is the next room we are going to walk into. It is the story of a man who wrote the best textbook on Copenhagen quantum mechanics that had ever been written, and who, in the process of writing it, found the cracks. It is also the story of a man who, for finding those cracks, was kicked out of the country of his birth and forced to spend the rest of his working life writing the rebuttal to Copenhagen from offices on other continents. We are not going to a hotel in Brussels for the next room. We are going to a small office in Princeton in 1951 with a 34-year-old assistant professor at the desk and an old man named Albert Einstein walking up the path outside. Part 5. Bohm rediscovers it. David Joseph Bohm was born on the 20th of December 1917 in Wilkes-Barre, Pennsylvania. He was the son of a Hungarian Jewish immigrant who ran a furniture store in a coal mining town during the years before the Great Depression. He studied physics at Penn State, then spent a year at the California Institute of Technology, then moved to the University of California at Berkeley to pursue his doctorate under J. Robert Oppenheimer, the brilliant and complicated physicist who would, a few years later, become the scientific director of the Manhattan Project. Bohm's doctoral work was on the physics of plasmas. The work was so directly relevant to the wartime nuclear weapons program that it was immediately classified. This created an absurd situation that has become part of the small folklore of mid-20th century American physics. Bohm had contributed calculations that fed into the design of the atomic bomb. But because his work was classified, and because he was a graduate student whose security clearance had been delayed, he was denied access to his own doctoral thesis. He could not read it. He could not defend it in the usual way. Oppenheimer had to personally certify to the University of California that Bohm had completed the research. The university granted Bohm his PhD based on Oppenheimer's word, not on Bohm's ability to defend the document he had written. After the war, in 1947, Bohm became an assistant professor of physics at Princeton University. He was 30 years old. He was working in the most prestigious physics department in the United States, a few minutes' walk down the road from the Institute for Advanced Study, where Albert Einstein spent his days. And in 1951, Bohm published a textbook. The textbook was called Quantum Theory, and it was, in its way, an extraordinary book. It became, almost immediately, the definitive graduate-level treatment of what was, by then, called the Copenhagen interpretation. Generations of physics students learned the Copenhagen interpretation from David Bohm's book. The book contained, among many other things, Bohm's careful reformulation of the famous Einstein-Podolsky-Rosen thought experiment, an argument that Einstein and two younger colleagues had published in 1935 to challenge the completeness of quantum mechanics. Bohm reformulated the argument in terms of spin measurements, in a way that John Stuart Bell would, a decade later, use as the basis for his own theorem. To this day, physicists cite Bohm's 1951 textbook as one of the clearest and most rigorous presentations of orthodox quantum mechanics ever written. And then something happened that the textbook histories of the field do not usually tell you about. Bohm gave a copy of his new book to Albert Einstein. The two of them began a series of conversations on the grounds of the Institute for Advanced Study, walking together, the aging father of relativity and the young assistant professor, talking about what was wrong with the theory that Bohm had just written the best exposition of. Einstein's influence on Bohm during these walks was specific. He did not express vague philosophical dissatisfaction with quantum mechanics. He pointed Bohm toward the specific weak points in the Copenhagen argument. He challenged Bohm to look again at the Einstein-Podolsky-Rosen paper, the paper Bohm had reformulated in his own textbook, and to think about what it was really saying. He told Bohm to look at von Neumann's impossibility proof, specifically, to look at it carefully, to ask whether it actually proved what it claimed to prove. The textbook that Bohm had written as a definitive defense of Copenhagen became, in his hands, the instrument of Copenhagen's most serious challenge. By taking the interpretation seriously enough to write a rigorous and complete treatment of it, Bohm had found the cracks. The very process of explaining the interpretation in full detail had revealed to him that beneath the mathematical formalism there was a layer of philosophical assumption that had never been justified by physics. Einstein had helped him see it, and what Bohm did next, in the year that followed, would cost him his career, his country, and his reputation in that order. What Bohm found, working alone in his Princeton office in late 1951, was that von Neumann's proof did not hold. Hidden variables were not impossible. You could construct a fully deterministic theory of quantum mechanics, in which every particle had a definite position at every moment, in which the trajectories of those particles were guided by the wave function, and in which the statistical predictions of standard quantum mechanics would emerge naturally from your ignorance of the particle's initial conditions. The randomness in this picture was not a feature of nature, it was a feature of your own knowledge. The universe was deterministic, the particles were real, their trajectories were definite, and the wave function, far from being a mathematical bookkeeping device, was a real physical entity whose behaviour was reproducible, predictable, and complete. On the 5th of January 1952, Bohm submitted 2 papers to the journal Physical Review. They were published the following month, in the issue of February 1st, 1952. The papers were titled A Suggested Interpretation of the Quantum Theory in Terms of Hidden Variables, Part 1, and A Suggested Interpretation of the Quantum Theory in Terms of Hidden Variables, Part 2. They appeared in Physical Review, Volume 85, pages 166 through 193. And what they did was something that the physics community had been told for the previous 20 years was mathematically impossible. They gave every particle a definite position. They described the evolution of those positions using a deterministic equation, a guidance equation that Bohm derived from the wave function itself. They introduced the concept of the quantum potential, a new kind of potential energy, derived from the wave function, which depends on the shape of the wave function, rather than its amplitude, and they showed, rigorously, that the statistical predictions of standard quantum mechanics emerged naturally when you took an ensemble of particles starting from slightly different initial conditions and let each one evolve under the guidance of the wave function. The math worked. Every prediction of standard quantum mechanics was reproduced exactly, not approximately, exactly. Imagine what it would be like to settle into a comfortable chair in a borrowed office in São Paulo, Brazil, in the early summer of 1952. The fan is turning. The light through the window is the soft, slanting light of the southern hemisphere in winter. You're 34 years old. You've just finished writing what you believe to be the most important papers of your career. They are about to be published in the most prestigious physics journal in your former country, in a country that has, for the last 2 years, treated you as a political threat. You have been suspended from Princeton. You have been arrested and charged with contempt of Congress for refusing to inform on your colleagues, including the man who supervised your doctoral thesis. You have been acquitted, but it does not matter. Princeton refuses to renew your contract. No other university in the United States will hire you. Albert Einstein has written letters of recommendation on your behalf. They have made no difference. You have, in October of 1951, accepted a position at the University of São Paulo. The United States Consulate has, on your arrival in Brazil, confiscated your passport. To work legally in your new country, you have been forced to take Brazilian citizenship, which means surrendering the American citizenship into which you were born. You will not be allowed to return to the United States as a citizen for the next 34 years. You have, with all of that in the immediate background, written from this office on this other continent the papers that lay out, in detail, the rebuttal to the philosophical framework that the country of your birth used to decide you were too dangerous to teach physics in. You write the line, deliberately and quietly understated, that your interpretation, in your words, will be seen to give the same predictions as the usual one. You finish the paragraph. You address the envelope. You are, although you do not yet know it, finishing the work that will outlive every reputation that exiled you. The reception to the papers when it came was not what Bohm had hoped. According to F. David Peat, whose biography Infinite Potential is the standard source for this period of Bohm's life, J. Robert Oppenheimer convened a meeting at Princeton specifically to find flaws in Bohm's papers. The meeting was a kind of informal physics seminar, attended by Oppenheimer and several of his colleagues. They worked through the papers together. They could find no mathematical error. They could find no internal inconsistency. They could find no prediction that disagreed with experiment. After extended discussion, according to Peat's biography, Oppenheimer announced to the group that if they could not disprove Bohm, then they must agree to ignore him. Wolfgang Pauli, who had objected to de Broglie's pilot wave theory at Solvay 25 years earlier, now called Bohm's reformulation of essentially the same theory, in his words, artificial metaphysics. Werner Heisenberg, in his published writing of the period, called Bohm's interpretation ideological. Niels Bohr, when asked about it, reportedly called Bohm very foolish. What is striking about that list when you read it carefully is what is absent from it. There is no mathematical refutation of Bohm's theory. There is no experimental result that distinguishes Bohm's theory from standard quantum mechanics and rules Bohm's theory out. There is no demonstration that the theory gives a wrong prediction for any phenomenon that has ever been measured. To this day, there is no such demonstration. The theory was not defeated on scientific grounds. It was dismissed by a small group of senior physicists who had staked their reputations on a different interpretation of quantum mechanics, and who could not, by the end of 1952, afford to admit that an alternative existed. The Princeton meeting, Pauli's metaphysics, Heisenberg's ideology, Bohr's foolishness. Those were the responses that the foundational physics community gave to a piece of mathematics that did exactly what 20 years of impossibility proofs had said could not be done. The cost was personal. Bohm moved from Brazil to Israel in 1955. He taught at the Technion in Haifa, where he met and married Sarah Wolfson. In 1957 he moved to England, first to the University of Bristol, and then, in 1961, to Birkbeck College at the University of London. In 1959 at Bristol, working with a younger physicist named Yakir Aharonov, he co-discovered what is now known as the Aharonov-Bohm effect, the demonstration that a charged particle can be affected by an electromagnetic potential, even in a region where the electric and magnetic fields are zero. The Aharonov-Bohm effect is one of the most important experimental results in 20th century physics. It is taught in every graduate course on quantum mechanics. It is in every standard textbook. The man who co-discovered it, in 1959, was an American physicist living in England because the country of his birth had decided he was too dangerous to be employed in. The textbooks today do not tell you why he was there. They do not tell you about the passport. They do not tell you about the contempt charge. They do not tell you about Oppenheimer's meeting. They name the effect, they show you the math, they move on. That pattern of taking from Bohm what the field could use and discarding what the field found threatening is the operational meaning of the word erased. The Aharonov-Bohm effect is in the textbook because it does not threaten the Copenhagen interpretation. It is a result about electromagnetic potentials in regions of zero field. It fits comfortably inside the existing framework. Bohm's 1952 papers, by contrast, give a complete alternative interpretation of all of quantum mechanics. They threaten the Copenhagen consensus directly. They are not in the textbook. The same author, the same physicist, the same lifetime, the same intellectual lineage. The two pieces of work treated differently because one of them is useful and the other one is dangerous. We are about to meet the physicist who first read those 1952 papers and understood, in detail, both their power and what it meant that they had been buried. His name was John Bell. He was an Irish accelerator theorist working at CERN, and what he did with what he read is the next step in the story. Part 6. The 12 Years of Silence. What happened to David Bohm's two 1952 papers in the dozen years after their publication is one of the most documented examples of institutional silence in the history of science. The papers existed. They had been peer-reviewed and published in Physical Review, the most prestigious journal in the field. They had survived Oppenheimer's hostile reading at Princeton without yielding a single mathematical error. They had not been refuted, and for 12 years, almost nobody in mainstream physics worked on what they implied. Graduate students did not write theses on pilot wave theory. Professors did not assign Bohm's papers in their quantum mechanics courses. Conferences on quantum foundations were not held because the field, by quiet consensus, had decided that there was no longer anything to do in quantum foundations. Quantum mechanics had been completed. The interpretation had been settled. The remaining work was applications. You did not ask what quantum mechanics meant. You used it. The mechanism by which this consensus was enforced is what the historian Olival Frere Jr. has documented in painful detail in his 1994 book The Quantum Dissident, and what James T. Cushing analysed in his 1994 book Quantum Mechanics, Historical Contingency, and the Copenhagen Hegemony. The mechanism was not a conspiracy. It was not a secret committee meeting somewhere deciding which papers would be allowed to appear in print. It was something both subtler and more effective than either of those things. It was a culture. It was a shared understanding transmitted from senior physicist to graduate student to junior faculty member that certain questions were not legitimate physics questions. If you wanted a career in physics, you did calculations, you computed cross-sections, you derived scattering amplitudes, you worked on the new high-energy theories that were emerging at Brookhaven and at CERN. You did not ask what your calculations meant. You did not ask what the wave function was. You did not ask whether particles had trajectories between measurements. Those were philosophical questions. Philosophy in a physics department was a career killer. Niels Bohr's institute in Copenhagen had, by the 1950s, become the central node of this culture. The physicists who passed through Copenhagen, and who then took faculty positions at universities all over Europe and the United States, carried with them a specific philosophical training. They had absorbed Bohr's complementarity. They had absorbed Heisenberg's argument that the act of measurement creates the result. They had absorbed the conviction that asking what quantum mechanics describes is the wrong kind of question. And they enforced this training, not always consciously, on the next generation of graduate students. The students who asked the wrong kinds of questions did not get the recommendation letters they needed. The students who asked the right kinds of questions, who did calculations, who computed, who applied, got the recommendation letters and got the jobs. There was, within this culture, a specific enforcer. His name was Leon Rosenfeld. He was a Belgian physicist who had been a close collaborator of Bohr's for decades. The historian Adam Becker, in his book What is Real, describes Rosenfeld as a kind of consigliere for the Copenhagen interpretation. Rosenfeld's role was to identify and to attack anyone in the foundational physics community who strayed from the orthodoxy. In 1968, a young German physicist named H. Dieter Zeh published what would later be recognized as the foundational paper on quantum decoherence, one of the most important concepts in modern physics. Rosenfeld wrote to Zeh's department head, calling the paper a concentrate of the wildest nonsense, and expressing what he characterized as a confidence that the paper had not been submitted with his superior's approval. Zeh had tenure. He kept his job, but his career stalled, and his graduate students for the next several years had a noticeably harder time finding employment than the graduate students of less heterodox advisors. Zeh said, later, that this was something he would never be ready to forgive. There was a parallel case 3 years later. In 1957, a Princeton graduate student named Hugh Everett completed his doctoral thesis under John Archibald Wheeler. The thesis proposed what we now call the many worlds interpretation of quantum mechanics. Wheeler, who was a tactful and politically astute physicist, had tried to soften Everett's thesis before submitting it to the field, rewriting sections and removing the most provocative language so that it would be palatable to Bohr. In 1959, Wheeler arranged for Everett to visit Copenhagen and present his interpretation. The visit was a disaster. Rosenfeld, who was present, wrote afterward that neither he nor Bohr had any patience with Everett, and that Everett was, in his words, extremely unintelligent. The reception in Copenhagen was hostile enough, and the prospects in mainstream physics academia were poor enough, that Everett left physics altogether. He went to work for the Pentagon on nuclear strategy. He never published another physics paper. He died in 1982 at the age of 51, overweight and an alcoholic. His daughter would later recall a distant and emotionally unavailable father. His many worlds interpretation, for decades, was treated as a kind of joke within mainstream physics, a science-fictional flourish that nobody took seriously. It would only be rehabilitated much later, in the 1990s and early 2000s, after Everett was already long dead, when the development of decoherence theory gave many worlds a kind of mathematical respectability it had not had during his lifetime. The parallel case to Bohm matters because it shows that what happened to pilot wave theory was not unique to pilot wave theory. It was a pattern. The pattern was that interpretations of quantum mechanics that challenged the Copenhagen orthodoxy got treated, by the most senior figures in the field, not as scientific proposals to be evaluated on their merits, but as ideological challenges to be marginalized. The marginalization worked. For 30 years after Bohm's 1952 papers, mainstream physics treated the question of what quantum mechanics describes as a closed question. The answer, the mainstream said, was that quantum mechanics does not describe anything. It predicts the statistics of measurement outcomes. Beyond that, asking is not allowed. The phrase that has come to summarize this culture, in the popular accounts, is shut up and calculate. It is often attributed to Richard Feynman, as though Feynman himself had laid down a kind of commandment to the field. Feynman did not say it. The phrase was actually coined by a physicist at Cornell named N. David Mermin, in an article in the magazine Physics Today in 1989. And Mermin was not endorsing the attitude. He was describing what had been done to him. As a graduate student at Harvard in the early 1960s, Mermin had tried to ask his professors about the meaning of quantum mechanics. He had asked, in essence, the kind of questions that David Bohm had asked. He had asked what the wave function was. He had asked what measurement meant. He had asked whether particles had trajectories between measurements. He had been told, in so many words, that asking such questions would prevent him from getting his doctorate. He had been told to stop thinking about these questions and start solving the problem sets. The shut up and calculate culture was something he had experienced as a student. The phrase, when he coined it in 1989, was his way of naming what had been done to him. It was the description of the institutional pressure, not a piece of wisdom about how to do physics. There were, in this period of silence, a few exceptions. Bohm himself, working from Brazil and then from Israel and then from England, continued to develop his interpretation throughout the 1950s and the 1960s. Louis de Broglie, in the mid-1950s, after reading Bohm's papers, returned, late in his career, to the pilot wave theory he had abandoned at Solvay. In 1956, he published a book on what he now called the double solution theory. In 1970, the very first article in the very first issue of the new journal Foundations of Physics, when it was founded, was a paper by Louis de Broglie. He had, in his late 70s, come full circle. He had returned to the theory he had originally proposed in 1927 and been forced by social and institutional pressure to abandon. He would die in 1987 at the age of 94, the last surviving participant of the Solvay Conference of 1927. By then, the central insight of his work had been waiting for 50 years to be examined again seriously by the field that had ignored it. The field would not begin to look again until John Stuart Bell, a working accelerator physicist at CERN, walked into a library one day in the mid-1960s, picked up Bohm's 1952 papers and read them carefully for the first time. What he read made him furious. We were about to walk into the office where he was sitting when he read those papers, and we were about to follow him through the decade in which his fury, slowly and methodically, became the most important theorem in the foundations of quantum mechanics. Part 7. Bell reads the papers. John Stuart. Bell was born on the 28th of July, 1928 in Belfast in Northern Ireland. He was the son of a working-class family in which neither of his parents nor any of his 3 siblings had completed secondary school. He decided at the age of 11 that he wanted to be a scientist, and he pursued that ambition with the kind of stubborn clarity that someone with very little safety net often pursues such things. He earned 2 bachelor's degrees from Queen's University Belfast, one in experimental physics in 1948 and one in mathematical physics in 1949. He spent a decade at the Harwell Atomic Research Establishment in England working on the design of particle accelerators. In 1960, he moved to the European Organisation for Nuclear Research, the laboratory we now call CERN, in Geneva, where he stayed for the rest of his life. At CERN, John Bell was a theoretical particle physicist. He worked on accelerator design, on the theory of particle interactions, on the kind of technical mathematics that made it possible for the experimental particle physics program at CERN to function. He published roughly 80 papers in high-energy physics over the course of his career. His colleagues at CERN respected him as a skilled and rigorous professional doing serious work in a serious field. What they did not know, for most of his career, was that in the evenings and on weekends and on his holidays, Bell was thinking about something that the physics community considered, at best, a waste of time and at worst evidence of a kind of intellectual instability. He was thinking about what quantum mechanics actually means. He was thinking specifically about David Bohm's 1952 papers. Bell had first read those papers sometime in the early 1960s, when he was already a working physicist with a young family in Geneva. He later described the experience of reading them. He used the word revelation. He had been told throughout his graduate training that the kind of theory Bohm was proposing was mathematically impossible. He had absorbed from his professors and from his textbooks the assumption that von Neumann had proved hidden variables impossible, and that Bohr and Heisenberg had shown, on philosophical grounds, that asking what particles were doing between measurements was meaningless. And now here, in Bohm's 2 papers in Physical Review, he was seeing the impossible done. Bohm had constructed a fully deterministic theory of quantum mechanics in which every particle had a definite position at every moment. Every prediction of standard quantum mechanics was reproduced exactly. The interference pattern in the double slit experiment was explained without invoking wave function collapse, without declaring that the particle goes through both slits, and without forbidding the question of which slit the particle actually went through. What struck Bell about Bohm's theory was not just the determinism, not just the recovery of definite particle positions, not just the trajectories. It was, in his words, the elimination of the observer. In Bohm's theory, the equations of motion of the particles did not include any reference to a measurement, to a measuring apparatus, to an observer, or to consciousness. The theory described in pure physical terms what was happening, regardless of who was or was not looking. Bell, who had felt since his student days that quantum theory was, in his own description, rotten, suddenly understood where the rot was. It was not in the mathematics. The mathematics was fine. The mathematics had been fine since Schrödinger had written down his equation in 1926. The rot was in the interpretation. The philosophy that the field had been layering on top of the working mathematics. The philosophy that said, particles do not have positions until you measure them, that the act of measurement creates the result, that the universe at its base is irreducibly random, that the question of what is happening between measurements is meaningless. All of that was, in Bell's view, an unnecessary and damaging addition. And Bohm had shown that a different philosophy, one with particles having definite positions and trajectories, and a wave function that guides them, worked exactly as well. What made Bell furious, when he understood what he was reading, was that nobody had ever told him about it. He had been taught the Copenhagen interpretation as though it were the only interpretation. He had been told the von Neumann proof was solid. He had not, in his graduate training, ever encountered the name Louis de Broglie in connection with anything other than wave-particle duality. He had not been told that, in 1927, at the most important physics conference of the 20th century, a different theory had been proposed in detail and answered in the room. He had not been told that, in 1952, an American physicist working in exile in Brazil had reconstructed the same theory and published it in Physical Review. He had been told that the question was closed, that the case was settled, that all the smart people in the field were already converged on the same answer. And it had been, when he opened the journals carefully and read for himself, not closed at all. It had been buried. He wrote about this experience repeatedly, with increasing frustration, over the next 3 decades. He asked in his published essays why Max Born, who had been a participant at Solvay, had never mentioned the pilot wave to him during the years when they were in correspondence. He asked why von Neumann had not considered the obvious counterexample to his own assumptions about non-commuting observables. He asked, most damningly, why physics textbooks were continuing to declare hidden variable theories impossible, and to cite the von Neumann proof as the reason. Decades after Bohm had published a working hidden variable theory that reproduced every quantum prediction, he noted that the field had performed what he called a fantastic somersault, from saying that hidden variables could not be done, to saying that hidden variables had been done but were trivially obvious, without ever pausing at the intermediate step of admitting that the field had been wrong. He pointed out, with a kind of dark humour, an irony in the terminology that had attached itself to Bohm's theory. The variables in pilot wave theory that the textbooks call hidden are, in fact, the positions of the particles, the things you actually see when you look at a detector screen, the actual clicks and dots that constitute every experimental result that has ever been recorded in the history of physics. Meanwhile, the wave function, the mathematical object that you never directly observe, is treated, in the Copenhagen interpretation, as the fundamental reality. The thing that is, in any operational sense, hidden gets called real. The thing that is, in any operational sense, real gets called hidden. The terminology itself, Bell observed, is a confession that the standard interpretation has its priorities backwards. His most famous contribution to physics, the theorem that bears his name, came out of this period of intense engagement with Bohm's papers. In 1964, Bell published a paper titled On the Einstein-Podolsky-Rosen Paradox in a short-lived journal called Physics. The paper proved a result of enormous consequence. It proved that no theory in which hidden variables are local, in which they only depend on what is happening in the immediate space-time neighbourhood of the particle, can reproduce all the predictions of quantum mechanics. Some experiments, the theorem showed, would give different statistical results, depending on whether you were using a local hidden variable theory or standard quantum mechanics. The difference would be measurable. You could go into a laboratory and test it, and in the decades that followed, that experiment was done again and again with increasing precision. The most careful versions, the so-called loophole-free Bell tests, were performed in 2015 by 3 independent groups in the Netherlands, in Vienna, and at the National Institute of Standards and Technology in Boulder, Colorado. All 3 groups got the same result. The local hidden variable theories were ruled out. Quantum mechanics was correct. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger, the 3 physicists who had led the experimental program testing Bell's inequalities over the previous 4 decades. The Nobel citation praised the experiments. It celebrated the proof that local hidden variables are not the way nature works. It didn't mention, in any of the press materials, that the theorem that motivated all of those experiments had been written by a physicist who had been working out of his fury at being kept ignorant of David Bohm's 1952 papers. It did not mention that Bohm's theory is, itself, a non-local hidden variable theory, and that Bell's theorem proves that any theory reproducing quantum predictions has to be non-local. It did not mention pilot wave theory at all. Bell himself had been reportedly nominated for the Nobel Prize in 1990, the year he died of a sudden cerebral hemorrhage in Geneva at the age of 62. The committee, however, had a long-standing practice of not awarding posthumous prizes, and Bell did not live long enough to see his own work formally honoured. The theorem he derived was celebrated. The reason he derived it was, and largely still is, not part of the public story. What Bell's theorem actually proves is the next room we need to walk into, because the textbooks and the popular accounts often present Bell's theorem as a refutation of Bohm. It is the opposite. Bell's theorem supports the kind of theory Bohm was proposing. It proves that the non-locality that Bohm's pilot wave introduces is not optional. It proves that any theory that reproduces the predictions of quantum mechanics has to have a non-local element. Copenhagen has it. Many worlds has it. Pilot wave has it. The theorem does not pick between them. But what it does, decisively, is rule out the kind of comfortable, local, classical view of reality that some physicists had been hoping to recover. The universe, Bell proved, is non-local. The question, after Bell, is not whether to admit non-locality. The question is what to do with it. And here, finally, we have the equipment we need to walk back into the basement in Toronto. We can talk now, in clean and unambiguous terms, about what the wave function does, about what the quantum potential is, about why an experiment with 80 trajectories on the cover of Science magazine was the single most important confirmation of de Broglie's 1927 proposal that anyone has ever performed. We're going to do that next. Part 8. What Bell's theorem actually proved. Bell's theorem is one of those results in physics that is famous in a slightly distorted form. You will see it referred to in popular accounts of quantum mechanics as the result that proves the quantum world is weird, or as the result that proves Einstein was wrong, or as the result that proves that hidden variables cannot work. The first of those is approximately right, in a loose sense. The second is incomplete. The third is simply incorrect. To see what the theorem actually proves, you have to take a step back and think about the question Bell was trying to ask. The question, in plain language, was this: could the universe be local? Locality in physics is the principle that the behavior of any particular object depends only on what is in its immediate space-time neighborhood. Nothing far away can directly affect what happens here, except by sending a signal that takes time to arrive. This is the kind of common-sense reality that everyone outside physics takes for granted. The lamp on your desk is not, in any direct way, affected by a star 50 light-years away. If something happens at that star, it takes 50 years for any information about it to reach you. Locality is the deep intuition that nothing influences anything else over a distance instantaneously. Quantum mechanics, since at least 1935, when Einstein, Podolsky and Rosen had published their paradox, had been suggesting that this intuition was in trouble. The paradox involved two particles that had been prepared together and then separated. If you measured certain properties of one particle, the standard formulas of quantum mechanics seemed to imply that the other particle, no matter how far away, immediately had correlated properties of its own. Einstein had famously called this spooky action at a distance, and he had used it as an argument that quantum mechanics had to be incomplete. There had to be, he thought, additional variables, hidden variables, that fully determined what each particle would do, and that the correlations were a consequence of the particles' shared history, rather than of any real instantaneous influence. What Bell did, in 1964, was to take Einstein's intuition seriously, and follow it out to its mathematical conclusion. He derived an inequality, a statistical relationship that any theory of local hidden variables would have to satisfy. The inequality places an upper bound on the correlations that can occur between distant measurements, if those correlations are produced by local hidden variables and nothing more. Quantum mechanics, as a mathematical theory, predicts that for certain experimental setups, the correlations would violate this inequality. In other words, the correlations would be stronger than any local hidden variable theory could account for. Bell's inequality is the line that locality is allowed to draw in the sand. The quantum predictions cross that line. So the question, after Bell, was no longer whether locality and hidden variables were compatible with quantum mechanics in principle. The question was which side was correct in practice. To find out, you had to do the experiment. The first reasonably definitive experiments were done by Alain Aspect in Orsay, France, in the early 1980s. They confirmed the quantum prediction. The correlations were stronger than any local hidden variable theory could produce. They violated Bell's inequality. Local hidden variables were ruled out. Over the next 3 decades, dozens of follow-up experiments tightened the result, plugged various loopholes, and in 2015, 3 independent groups produced what came to be called the loophole-free Bell tests. Ronald Hansen's group in Delft published in Nature on the 21st of October 2015, with 96 entangled electron spin pairs and a statistical significance just above 2 standard deviations from the local hidden variable prediction. Marissa Giustina's group in Vienna published in Physical Review Letters in December 2015, with a violation at roughly 11 standard deviations. Lyndon Christa Schalm's group at the National Institute of Standards and Technology in Boulder published in the same issue of Physical Review Letters with a violation at roughly 7 standard deviations. The result was unambiguous. The universe is not local. Locally hidden variables cannot describe nature. This is what Bell's theorem proves. And here is the part that the textbooks consistently fail to convey clearly. The theorem rules out local hidden variables. It does not rule out non-local hidden variables. It does not rule out hidden variables in general. Bohm's pilot wave theory is, by construction, a non-local hidden variable theory. The quantum potential, the field that guides the particle in pilot wave theory, depends on the configuration of all the particles in the system, not just on what is happening at the particle's immediate location. When two particles are entangled, the quantum potential connects them across whatever distance separates them instantaneously. This is not a flaw of the theory. It is the central feature of the theory. The theory is non-local. The theory predicts the violation of Bell's inequality. The theory survives every experimental test of Bell's theorem. Bell's theorem is, in fact, perfectly consistent with pilot wave theory. The theorem rules out the kind of theory that the people who dismissed pilot wave at Solvay would have considered more comfortable. It does not rule out pilot wave itself. What the theorem does prove, decisively, is that any theory that reproduces quantum predictions has to incorporate some kind of non-local influence. This is a statement about every interpretation of quantum mechanics, not just about pilot wave theory. The Copenhagen interpretation has to be non-local. Many worlds has to be non-local. Pilot wave is non-local. Cubism is non-local. Every interpretation has to live with the consequence that nature, at the quantum level, supports correlations that are stronger than any local mechanism can account for. The interpretations differ in how they describe the non-locality. They do not differ in whether to admit it. For the Copenhagen interpretation, the non-locality is, in a sense, hidden in the act of measurement. When you measure one particle of an entangled pair, the wave function of the joint system instantaneously collapses, and the distant particle's wave function changes as well. The Copenhagen account does not explicitly tell you that anything is being signalled. It just tells you that the wave function has updated. The non-locality is real, in the sense that the correlations cannot be explained by anything local, but Copenhagen does not commit itself to a physical mechanism that is doing the connecting. For many worlds, the non-locality is hidden in the branching structure of the universal wave function. When you measure one particle, you split into branches in which you got different measurement outcomes. The distant particle, in each branch, has the correlated outcome that you would expect. There is no instantaneous signal travelling between the particles. The correlations are an artifact of which branch each version of you ends up in. But you have to commit in many worlds to the reality of every branch of the wave function and to a kind of cosmic structure in which the universe is constantly splitting into uncountably many copies. For pilot wave theory, the non-locality is explicit. The wave function is a real physical entity, and it lives in a high-dimensional space that connects the configurations of all the particles in the system. The quantum potential, derived from the wave function, depends on the positions of all the particles at once. When you measure one particle, the wave function updates everywhere, and the quantum potential acting on the distant particle changes accordingly. There is, in pilot wave, a real, identifiable, physical thing that is doing the connecting. The wave function is the connection. The non-locality is not a mystery or an emergent feature. It is the explicit content of the theory. This is the part that physicists, in general, find deeply uncomfortable. Pilot wave theory makes the non-locality of quantum mechanics into a concrete physical fact. It tells you, in plain mathematical language, what the wave function is doing and how it is connecting distant particles. The Copenhagen and many worlds interpretations both contain non-locality, but they obscure it. Pilot wave displays it, and once you display it, you have to confront the fact that you do not really know what the wave function is. You can describe what it does. You can write down its equations. You can compute from those equations every prediction that quantum mechanics makes. But you cannot say, in any deep sense, what kind of thing the wave function is, whether it lives in physical space or in a more abstract configuration space, whether it is a field, a substance, an information structure, or something else entirely. The wave function is, in this sense, the unknown variable at the heart of physics. Bohm's theory makes the wave function real and visible. Copenhagen makes the wave function disappear into the measurement formalism. Many worlds makes the wave function so comprehensive that it includes every possible history. None of the three interpretations tell you what it is, and it is, in pilot wave theory, the thing that has been steering every particle in the universe since the Big Bang. What that means for the double-slit experiment is now something we can describe precisely. Now that we have the conceptual machinery in place, we can walk back into the basement in Toronto. We can look at the apparatus. We can describe step by step what happens to a single photon as it makes its way from source to detector. And we can read the trajectories that Sasha Coxis and his colleagues reconstructed in the way they were meant to be read, not as decorative figures, but as a photograph of pilot wave theory at work. That is the next step. We're going to walk a photon through the experiment together, and then we're going to look at the data. Part 9. What the wave function actually does. Imagine for a moment that you are the photon. Imagine you are one of the single photons that the team in Toronto fired through their apparatus. You begin your life at the surface of a tiny semiconductor crystal, a few atoms across, inside a cryostat at very nearly the temperature of liquid helium. The crystal has just been struck by a pulse of the 810 nanometer pump laser, and in response you have been emitted, a single quantum of light at a wavelength of 943 nanometers, with a frequency in the near-infrared just below the threshold where human eyes can see. You leave the crystal. You travel down a single-mode optical fibre. You arrive at a 50-50 fibre beam splitter, which in this experiment is functioning as the two slits. In the picture you grew up with, the textbook picture, the standard Copenhagen account, what happens next is unspeakable. You do not have a definite position. You do not go through either slit. You're not anywhere in particular. You're described by a wave function, and the wave function passes through both slits, and you, the photon, are smeared out across both outputs in some kind of indefinite quantum superposition. When you eventually arrive at the detector, you will be found at some definite location, but until that moment, the question of where you were is, in the standard story, not a meaningful question. In the pilot wave picture, what happens is different. You do have a definite position. You always have a definite position. You came out of the source at a specific point on the crystal, and you have been travelling along a specific trajectory ever since. When you reach the 50-50 beam splitter, your trajectory takes you through one of the two outputs. Which output depends on your initial position, your initial momentum, and the configuration of the wave function around you, but it is determined. There is, at every moment, a specific output that you are about to take. Let us say you take the left output. You emerge from the left slit of the apparatus. The other output is empty of you. There is no part of you on that side. There is only one of you. You have a position. You went through one slit. But, and this is the central piece, the wave function that is associated with you, the wave function that evolves according to Schrödinger's equation, does not behave the way you do. The wave function passes through both outputs. It does what waves do. It spreads. It propagates. It interferes with itself on the far side of the beam splitter. Where the wave function from the left output and the wave function from the right output add constructively, there is now a region of high amplitude. Where they cancel destructively, there is a region of low amplitude. The wave function on the far side of the beam splitter is, at this point, a landscape of bright and dark zones, the same kind of interference pattern that Thomas Young saw on his screen in 1801. The wave function has explored both paths. Now the wave function is not just a pattern. In the pilot wave picture, it is a real physical entity. And it does something specific. It gives rise to what David Bohm called the quantum potential. The quantum potential is a kind of potential energy, but it is a strange kind. It is derived from the wave function, but unlike the potentials you might be familiar with from classical physics, it does not depend on the amplitude of the wave function. It depends on the shape. This has a remarkable consequence. The quantum potential does not get weaker with distance the way an electromagnetic field does. It does not fall off with the inverse square of the distance the way gravity does. Its strength is determined by how the wave function curves, and a wave function that is small in amplitude can still curve sharply and produce a strong quantum potential. The quantum potential is, in this sense, a holistic field. It carries information about the entire configuration of the experiment instantaneously, without weakening over distance. You, the photon, are now propagating through the region on the far side of the beam splitter. You have a definite trajectory. You are being pushed and pulled by the quantum potential, which itself is being shaped by the interference of the wave function. In the bright zones of the wave function, the quantum potential gently steers you toward the center of the bright zone. In the dark zones, the quantum potential steers you away. You curve, you undulate, you move along a trajectory that, because the quantum potential is the holistic field that it is, takes into account both slits at once, even though you only went through one. The wave that went through both slits has built the landscape that is now guiding you. The wave function explores. The particle navigates the landscape that the exploration produced. 8 meters later, you arrive at the detector. You land at some specific position, a dot. Tomorrow, the laser will fire again, and another photon will make the same journey, starting from a slightly different position on the crystal, going through one or the other slit, being guided by a similarly shaped wave function, ending up at some other specific position on the detector. Over many photons, the collection of dots reproduces exactly the bright and dark band interference pattern. Each individual photon went through one slit. The wave function went through both. The two of them together made the universe look quantum. There is a simple analogy that helps to picture this. Imagine a river that splits into 2 channels around an island, and then those 2 channels rejoin on the other side. A boat is going to travel from one end to the other. In the standard Copenhagen account, the boat does not exist between the entry point and the exit point. It is smeared out across the entire river system in some indefinite way until it is observed at the exit. In the pilot wave account, the boat is a real boat, with a real captain going down one of the 2 channels. But the river itself, which flows through both channels and rejoins in patterns of currents and eddies, on the far side, is what determines where the boat ends up. The boat is in one channel. The river is everywhere. The boat is steered by the river. The river was shaped by the geometry of both channels at once. The boat went through one. The river went through both. The non-locality, in this picture, is the property of the river. The river updates everywhere when the geometry changes. If you place a stone in the right channel, the eddies on the far side change, and the boat in the left channel, which has not gone anywhere near the stone, is steered along a different path because the river it is riding has a different shape. This is what entanglement looks like in the pilot wave picture. 2 particles, 2 boats, in 2 channels. A shared river that connects them. When you measure one particle, you put a stone in its channel. The shared river updates. The other particle is steered differently. The correlation is real. The mechanism is the river. The river is the wave function. The wave function is real. This is the picture that de Broglie proposed in 1927, that Bohm reconstructed in 1952, that Bell argued his entire career was a coherent and beautiful and ignored alternative to the Copenhagen account. It is the picture that, when Sascha Coxis and his colleagues in Toronto reconstructed 80 average photon trajectories in 2011, finally appeared in laboratory data. The trajectories curve, they undulate, they cluster in the bright fringes, they avoid the dark ones. They never cross the center line. Each trajectory takes one of the 2 slits. The wave function takes both. The collection of trajectories looks exactly like de Broglie's hand-drawn diagrams from his Sorbonne thesis 87 years earlier. The data, when you read it carefully, is a photograph of the river. Now the question that an honest reader of this story should be asking is, why is the picture I just described not in the textbook? The Copenhagen and the pilot wave interpretations both reproduce the same predictions. They both account for the data. The pilot wave is, if anything, easier to picture easier to teach, easier to use as a starting point for further questions about what the wave function is and what it is doing. Why has the field for a century chosen the harder option? Why has it told students that the question of which slit the particle went through is meaningless, when there has been, since 1927, a perfectly coherent way of saying that the particle went through one slit and the wave went through both? We're about to walk back into the Toronto basement in full. We're going to look at the 80 trajectories on the cover of Science magazine, and then, after we've seen them in their proper light, we're going to ask the question that the entire arc of this story has been building toward. We're going to ask why the textbooks did not change. Part 10. The Toronto Experiment in full. Let us walk into the basement now. Ephraim Steinberg's lab at the University of Toronto sometime in the spring of 2011. The lab is part of the Centre for Quantum Information and Quantum Control. Steinberg himself is, by this point, a senior figure in the field of experimental quantum optics. He received his doctorate from the University of California at Berkeley, working under a physicist named Raymond Chiao on the question of how long it takes a photon to tunnel through an optical barrier. He studied, after his doctorate, at the École Normale Supérieure in Paris under Serge Haroche, who would go on to win a Nobel Prize for his work on the manipulation of individual quantum systems. Steinberg's 1996 doctoral thesis won the American Physical Society's prize for the best doctoral thesis in atomic, molecular and optical physics that year. He is not, by any reasonable measure, an outsider. He is in the top tier of his field, running one of the most precise optical labs in Canada, with the funding and the institutional backing that comes with that position. When his lab decides to attempt a measurement, the field pays attention. The measurement they attempted is now what you would expect, but the technique is worth pausing on, because the technique is what made the experiment possible. The technique is called weak measurement. It was first proposed in 1988 in a paper by three physicists named Yakir Aharonov, David Albert, and Lev Weidman. Yakir Aharonov is the same physicist who, 29 years earlier, had worked with David Bohm at the University of Bristol on the Aharonov-Bohm effect. This is not a coincidence. Aharonov was one of the few physicists in the world who had spent decades carefully thinking about what quantum mechanics describes and what kinds of measurements you can make on it, without dismissing the underlying questions as illegitimate. Weak measurement is, in a real sense, the experimental technique that grew out of that decades-long line of careful thinking. The basic idea of weak measurement is this. In an ordinary quantum measurement, you couple your measuring device to the quantum system strongly. The coupling is strong enough that the measurement extracts a definite value from the system. It is also, by virtue of the uncertainty principle, strong enough to disturb the system. After a strong measurement, the future evolution of the system has been altered. You cannot ask in a single shot both where the particle is and what its momentum is, because measuring one of those quantities decisively disturbs the other. This is the source of the textbook claim that you cannot follow a particle's trajectory through the double slit. Each measurement of position kicks the particle hard enough that its onward path is changed. In a weak measurement, you couple the measuring device to the system only weakly. The coupling is so gentle that any individual measurement extracts almost no information. The signal in any single shot is buried under the noise. But, and this is the key insight, if you repeat the weak measurement on a large ensemble of identically prepared particles, the noise averages out. The mean signal, the average over the ensemble, gives you the expectation value of the observable you are measuring, at the spatial location where you measured it, without disturbing the future evolution of any individual particle enough to spoil the experiment. The interference is preserved. The trajectory information accumulates in the ensemble average. You get both. In 2007, a physicist named Howard Wiseman, working at Griffith University in Australia, proved a theorem that is the foundation of what happened next. Wiseman showed that if you perform a weak measurement of velocity at a given point in space, on a large ensemble of identically prepared particles, the average value you extract is exactly the Bohmian velocity. Not approximately, not coincidentally, exactly. The theorem says that the standard quantum formalism, the same formalism that Copenhagen physicists use to compute their statistical predictions, picks out one and only one trajectory field as the answer to the question of what the average velocity at a given point in space is. And that trajectory field is the de Broglie-Bohm velocity field. There is no other trajectory field consistent with the data of a weak measurement of velocity. The mathematics that everyone agrees on, the mathematics that Copenhagen physicists use every day, contains within it, as a theorem, the Bohmian trajectories. Steinberg's group, in their 2011 experiment, took Weismann's theorem and turned it into a laboratory measurement. The apparatus was elegant. The single photon source was a liquid helium-cooled indium-gallium arsenide quantum dot inside a gallium arsenide and aluminum arsenide micropillar cavity, fabricated at the National Institute of Standards and Technology in Boulder. The single photon source was pumped with 810 nanometer laser light and emitted single photons at 943 nanometers. The single photon purity was verified through a Hanbury-Brown twist correlation measurement, which returned a value of G squared at 0 of 0.17 plus or minus 0.04. This is well below the half threshold that certifies genuine single photon emission. Each event in the detector corresponded to exactly one photon. The double slit was implemented, as I described in the previous part, as a 50-50 fibre beam splitter, with the two output beams acting as the two slit sources. The key element of the experiment was a thin 0.7 mm slab of calcite crystal, whose optic axis was oriented at 42 degrees to the polarization axis of the incoming photons. The calcite crystal created an almost negligible coupling between the photon's polarization state and its transverse momentum. The coupling was so weak that it did not perturb the interference pattern on the detector, but over many photons, the average shift in the polarization encoded information about the average transverse momentum at the spatial location of the crystal. After the calcite, the photon passed through a quarter wave plate and a beam displacer, which read out the circular polarization component. A cooled charge-coupled device camera recorded the position of each detection event. The team repeated the experiment thousands of times at each of 41 different imaging planes, spaced from 2.75 meters to 8.2 meters from the slit outputs. At each plane, the average transverse momentum was extracted from the weak measurement data. From the average momentum, by integration along the direction of propagation, the team reconstructed the average velocity. From the average velocity, by integration over the propagation length, they reconstructed the trajectories, 80 trajectories, plotted from the slits to the final imaging plane, 8.2 meters downstream. The trajectories begin at the two slit outputs. Near the source, they travel roughly straight. As they propagate, the interference of the overlapping wave functions begins to assert itself. The trajectories begin to curve, they undulate, they cluster together in the bright fringes of the interference pattern, and they diverge away from the dark zones. The trajectories starting from the left slit arc rightward, but only toward the nearest bright fringe. The trajectories starting from the right slit arc leftward in the same way. The overall pattern looks like a flowing river splitting into braided channels, and critically, no trajectory from the left slit ever crosses the center line of the apparatus. No trajectory from the right slit ever crosses to the left. The symmetry axis is an impenetrable boundary. Each photon stays on its own side. The paper, when it was written up, states the result explicitly. The trajectories measured in this fashion reproduce those predicted by the de Broglie-Bohm interpretation. Ephraim Steinberg himself, when he was interviewed by Nature News at the time, was characteristically careful in how he described the result. He said the measured trajectories were consistent with the interpretation advocated by Bohm and de Broglie. He said he was delighted to be able to see, in some sense, what a photon does as it moves through an interferometer, something he had been told all his life was impossible. He also said, more candidly than most physicists in his position would risk, that he and his generation of physicists had been brainwashed into thinking that measuring trajectories in the double slit was impossible. brainwashed. His word. And then he was careful to describe himself, in the same interview, as a professed agnostic on the question of which interpretation of quantum mechanics is correct. The trajectories, he pointed out, are derivable from standard quantum mechanics through Weismann's theorem without invoking the de Broglie-Bohm interpretation. The math gives you these trajectories. Whether they are real, in some deeper ontological sense, is a separate question that the data does not by itself settle. This care is important. The experiment did not prove that pilot wave theory is true. It did not prove that Copenhagen is wrong. What it proved is that the trajectories that de Broglie and Bohm and Bell had been describing for nearly a century are not mathematical fictions. They are physically reconstructible from data. They are visible. They can be photographed. Whether you choose to call them real or to treat them as a statistical curiosity that happens to fall out of the mathematics is a philosophical commitment that the experiment did not force. But what the experiment did force is the recognition that the trajectories are there. They are not nothing. They are in the data. They look exactly like what the pilot wave picture says they should look like. Steinberg's group did not stop. In 2016, they published a follow-up paper in Science Advances. This follow-up addressed the most stubborn historical objection to pilot wave theory, an argument that had been made in 1992 by Berthold Georg Englert, Marlon Scully, Georg Sussman, and Herbert Walter. Their argument was that, in entangled which-way variants of the double slit, the Bohmian trajectories were, in their words, surrealistic. The which-way detector would report that the particle had gone through one slit, while the pilot wave's trajectory said it had gone through the other. This had been treated in the popular literature as a kind of reductio ad absurdum of pilot wave theory. The 2016 experiment showed that the apparent surrealism is explained by quantum non-locality. The entangled partner's measurement disturbs the trajectory assignment, not because the trajectory is wrong, but because the particles are connected non-locally, and the which-way detector's report cannot be trusted in the way the objection had assumed. The objection dissolved. The trajectories survived. In 2022, the same group published a further extension in Nature Communications, showing that Bohmian trajectories of photons can be reconstructed even when relativistic effects are included. So let us take stock of where the trajectories stand. They were proposed in 1927. The proof that they were mathematically impossible was published in 1932. The refutation of that proof was published in 1935. The detailed theory of how to use them was published in 1952. The theorem connecting them to the standard quantum formalism was published in 2007. The experiment that visualized them in laboratory data was published in 2011. The defense of them against the strongest objection was published in 2016. The extension to relativistic regimes was published in 2022. At every step, the pilot wave picture has survived every test that has been thrown at it. It has been refined. It has been challenged. It has been confirmed. It has, after a century of work, become a coherent, mathematically complete, experimentally supported account of what is happening between emission and detection in the most famous experiment in physics, and the textbooks have not changed. Why? That is the question we cannot put off any longer. That is the question we are going to ask next. Part 11. Why the textbooks did not change. There is a survey, conducted in 2024 and published in the journal Foundations of Science, that asked working physicists which interpretation of quantum mechanics they preferred. The Copenhagen interpretation won, again, with about 39% of the responses. The de Broglie-Bohm pilot wave received about 2%. The authors of the survey noted in the discussion of their results that the persistent preference for Copenhagen likely reflects educational emphasis and what they called pragmatic appeal. In other words, people prefer what they were taught. The pattern that started at the Solvay conference in 1927, in which the Copenhagen group won by personality and momentum and not by mathematical argument, is now self-perpetuating. Students learn Copenhagen. They become professors. They teach Copenhagen. Their students learn Copenhagen. The loop has been running for almost 100 years. There is a more interesting number, however, hidden in the same set of surveys. When you ask not the general population of physicists, but the specialists in quantum foundations, the people who think professionally and at length about what quantum mechanics actually describes, the numbers change. The most recent Nature Interpretation Survey in 2025 found that only about 20% of foundation specialists preferred the Copenhagen interpretation. The other 80% were spread across many worlds: pilot wave, cubism, relational quantum mechanics, objective collapse theories, and various hybrid or in-between positions. The people who have looked the hardest at the question are the least likely to accept the interpretation that the textbook still teaches. The physicist and writer Sean Carroll has called this set of survey results the most embarrassing graph in modern physics. It is embarrassing not because it shows any particular interpretation winning. It is embarrassing because, a century after the field supposedly settled the question, the field has not settled the question. It has only stopped asking. That is the deeper answer to why the textbooks did not change after the Toronto experiment. The textbooks did not change because the people who write them are not in the habit of asking the question that the Toronto experiment answered. The textbooks treat the foundational interpretation as if it had been decided in 1927. The Toronto experiment, if you have not been thinking carefully about the foundations of quantum mechanics for a long time, looks like a clever optics result rather than a confirmation of a buried theory. The popular accounts of the experiment when it came out mostly characterized it as a curious illustration of weak measurement, or as a beautiful piece of experimental art, rather than as a confirmation of de Broglie's 1927 proposal. The fact that the trajectories matched the Bohmian prediction was acknowledged. The implication that the dominant interpretation had been resting on assumptions that were not necessary was, by and large, left for later, and later, of course, did not come. The infrastructure of the suppression has a long history. The historian David Kaiser at the Massachusetts Institute of Technology documented part of it in his 2011 book, How the Hippies Saved Physics. Kaiser's story is that, by the late 1960s and early 1970s, mainstream physics had become so hostile to foundational questions that the work was being done outside the mainstream by an unusual group of physicists in Berkeley, California. The group called itself the Fundamental Physics Group, with the word physics spelled with an F to underline the slightly countercultural flavour of the project. They had been founded in 1975 by a group of younger physicists who could not find jobs in mainstream quantum foundations because mainstream quantum foundations had been told there was no such thing. The discussions of the Fundamental Physics Group, in their weekly meetings at the Lawrence Berkeley National Laboratory, contributed directly to the development of the no-cloning theorem, to the practical foundations of quantum cryptography, and to the early development of the modern field of quantum information. None of that work would have happened, on the timescale that it did, if the Fundamental Physics Group had not existed. And the group existed because mainstream physics had refused to do the work itself. The historian Olival Frere Jr., in his 2015 book The Quantum Dissidents, documented the same pattern from a different angle. Frere showed that, in the 1950s and 1960s, research on quantum foundations was actively suppressed. Not by a formal conspiracy, not by a secret committee, by a culture in which graduate advisors told their students not to ask certain questions if they wanted careers, by tenure committees that quietly declined to promote junior faculty members whose research touched on the foundations, by journal editors who declined, with apologies, to publish papers on the interpretation of quantum mechanics, on the grounds that such papers were philosophy rather than physics. The suppression was diffuse, it was largely informal, it was by virtue of being diffuse and informal, very nearly impossible to point at and complain about, and it was very, very effective. James T. Cushing, the philosopher of physics at the University of Notre Dame, made the argument explicit in his 1994 book, Quantum Mechanics, Historical Contingency and the Copenhagen Hegemony. Cushing's argument was simple. The Copenhagen interpretation's victory was historically contingent. It was not the inevitable consequence of the physics. A slightly different set of social circumstances, a more assertive Louis de Broglie, a less hostile reception for David Bohm, a John von Neumann who had double-checked his own proof before publishing it, and the entire field might have developed along pilot wave lines from the beginning. The same experiments, the same data, a completely different understanding of what the data means. Copenhagen won, Cushing argued, not because it was correct, but because it was first and loudest, and because the dissenters were systematically marginalized. John Bell himself wrote about this repeatedly in the last decade of his life. He wrote that many physicists had come to hold, in his words, that it was not just difficult but wrong to look for a coherent picture of quantum reality, and that doing so was, if not actually immoral, at least unprofessional. He coined a small joke. He said he was, at CERN, a quantum engineer, but on Sundays he had principles. It was a self-deprecating remark, but the joke contained the entire problem. You had to treat foundational physics as a hobby that you indulged on Sundays. You had to keep your real opinions hidden during business hours. You had to pretend, in your professional life, that the question of what quantum mechanics means was not important, or at least not something you should be caught thinking about in the office. Bell carried the burden of this culture his entire career. He never had a job that was formally devoted to foundations. He never had graduate students in foundations. He never had a research budget for foundations. He published all of his most important foundational papers, including the famous 1964 theorem, while drawing his salary as a particle theorist on the CERN accelerator team. He died of a sudden cerebral hemorrhage on the 1st of October 1990 in Geneva at the age of 62. He had reportedly been nominated for the Nobel Prize that year. He did not live to see the prize awarded for any of his work. The 2022 prize for the experimental tests of his inequalities was, of course, posthumous from his perspective. Bell did not get to see the trajectories that vindicated his career-long argument. They appeared in laboratory data 21 years after his death. The persistence of the Copenhagen orthodoxy in the textbook is not, in the end, a story about evidence. It is a story about institutional inertia. It is a story about how a community of very smart people, given a moment of intellectual choice in 1927, made a choice for reasons that had to do with personality and social momentum, and then spent the next century building the choice into the architecture of their training programs. The choice became invisible. The alternative became unmentionable. The students absorbed from the textbooks and the lectures and the casual remarks of their advisors an entire metaphysical framework that they were not invited to examine. The metaphysical framework went eventually out into the broader culture, where it became one of the most successful and consequential pieces of philosophical export in the history of science. The notion that reality at its base is fundamentally unknowable, that observation creates the world, that the universe at the quantum level is genuinely random and indeterminate, has shaped the way 2 or 3 generations of educated people think about the relationship between mind and world. It has shaped popular books, films, novels, religious movements, theories of consciousness. It has done all of that on the back of a philosophical commitment that, the evidence has been suggesting for 100 years, was never required by the physics. The room moved on. In 1927, the room was a hotel meeting in Brussels, and it moved on because de Broglie was quiet and Bohr was loud, and the Copenhagen group had momentum and a charismatic leader. In 2011, the room is the entire profession of physics, in every country, and it moved on for the same reasons it moved on a century earlier. The argument has not been engaged, the data has been acknowledged, the textbook has not changed, the third layer is in the journals, it is not in the courses. That is not because the third layer is wrong, it is because the room is the way the room is, and the room is, in this case, 99 years late on a question that has not been particularly hard to look at since the answer was first proposed. Which leaves you and me in a strange place. The work has been done, the theory has been built, the mathematics has been checked, the experiment has been run. And the implication, for what reality actually is, has been deferred to a generation of physicists who have not yet been told they are allowed to think about it. We are about to ask, in the final part of this video, what that implication actually is. We are about to ask what the wave function is. We are about to ask what it is made of. And we are going to find that the answer, after a century of work, is that we do not know. Not because the data is insufficient, not because the math is wrong, because the question was never allowed to be asked in the first place. That is what we will look at together in the final part of this story. Part 12. What the wave function is made of. So we come back to the camera in the basement. 80 trajectories on the cover of Science magazine, curving, undulating, clustering in the bright bands, avoiding the dark ones, as though something is steering them, guiding them. We started with that image at the beginning of this story, and we are ending with it now. But the image is different now because you and I have walked the path between then and now together. We know, now, what is on those 80 lines. We know that each one is the average trajectory of a photon that went through one of the two slits, guided by a wave that went through both. We know that the trajectories are the photograph, in laboratory data, of a theory that was proposed by Louis de Broglie in 1927, that was rediscovered by David Bohm in 1952, that was defended by John Stuart Bell for the last 25 years of his life. We know that the trajectories are what they look like. We know what was on the line that the textbooks did not draw. What we do not know is what the wave function is. The wave function is the thing that, in this picture, has been steering every particle in the universe for as long as the universe has been here. It is the thing that connects the configuration of the entire apparatus to the trajectory of each individual particle. It is the thing whose interference passes through both slits, while the particle takes only one. It is, in pilot wave theory, a real physical entity. And nobody, in the entire history of physics, has been able to tell you what kind of thing it is. We have a name for gravity. We have a name for electromagnetism. We have approximate theories of the strong and weak nuclear forces. We have placeholders for dark matter and dark energy. We do not have a name for the wave function. We do not know if it lives in physical space or in a higher dimensional configuration space. We do not know how it relates to gravity, to space-time, to the fabric of the cosmos. We do not know whether there is one wave function for the universe, or whether each system has its own. We have spent a century deriving equations that describe what the wave function does, and we have spent a century telling students not to ask what the wave function is. This is the existential weight of the story. Not that the universe is more mysterious than you were taught. The universe is, in this picture, less mysterious than you were taught. It is knowable. It is deterministic. It has trajectories and definite positions and a wave function whose evolution can be calculated to extraordinary precision. The mystery is not in the data. The mystery is in the choice that was made, 100 years ago, to label the question of what the wave function is as a question that was not allowed to be asked, and to label the people who insisted on asking it as embarrassments to be quietly worked around. Louis de Broglie, the Duc de Broglie, sat in Paris from 1927 until his death in 1987, carrying the answer he had been given correctly in the room and watching it be ignored. David Bohm sat in São Paulo, then in Haifa, then in Bristol, then in London, watching his name attached to an effect in the textbook, and his theory absent from the same textbook, until his death in 1992. John Bell sat at CERN, working as a particle theorist by day, and arguing for the third layer on weekends, until his sudden death in 1990. Greta Hermann sat in a German philosophy journal, with the correct mathematical proof for 30 years, with no one reading. Every photon you have ever seen, every photon that has carried any image you have ever held in your mind, was, in this picture, steered by a field that has no name, by a field that the field of physics has spent a century telling its students not to ask about. That is the weight. That is what is heavy. When this video began, I told you there was a third layer to the most famous experiment in physics. The third layer is real. The third layer is in the journals. The third layer has been waiting for you to look at it, and it turns out, when you finally walk up to the third layer and look at it carefully, that there is a fourth layer underneath, and a fifth, and a sixth, all of them in the same direction, all of them pointing at the same unanswered question. What is the wave function? The third layer is the door, not the destination. We have opened the door. The room behind it is still mostly empty. The work of filling that room will fall to a generation of physicists who have not yet been told they are allowed to do it. Maybe you are one of them. Maybe someone you know is one of them. Maybe a child somewhere listening tonight is one of them. The answer is in there. The work is in there. The mystery, the real mystery, the one that has been steering every particle in the universe for 13.8 billion years, is in there. And we still do not have a name for it. Something is steering it. Something has been steering it since the beginning, and we are, all of us, finally just beginning to look